Hello everyone, I'm going to present you a short introduction to the Chapel's DistributedBag module, which provides a specialized data structure for unbalanced research at scale. So why do we need such a specialized data structure? So in fact, in some research fields, such as combinatorial optimization, we are solving problems using tree-based methods like backtracking or branch and bound. And those methods usually exhibit large and irregular trees. Okay? And so their parallel implementation generally raise two main challenges that are memory management and load balancing. Both are closely related to the data structure and generally represent the main complex parts of the parallel implementations. So the DistributedBag data structure provided by the DistributedBag packet module of Chapel aims at facilitating the user experience by managing transparently both challenges. So it provides a parallel safe distributed multipool specialized for deep first search because it is well known for its memory efficiency, along with a dynamic load balancing mechanism based on work stealing. So in few words, the data structure owns multiple pools, one per task, and when one pool gets empty during parallel execution, work stealing takes place. So if you want more details about the design and implementation, I recommend you to check the reference at the end of the talk. So now I'm going to show you a small code demonstration, which is a DistributedBag-based distributed multi-core branch and bound applied to the permutation flowchart scheduling problem. So for this small code demonstration, I prepared a sequential version of the branch and bound method for the permutation flowchart scheduling problem, and I tried to hide as much as possible all the logic associated to the problem and the branch and bound in order to make the code clear and to focus more easily on the data structure aspect. So first of all, we initialize the problem-specific data using classes. We also create the work pool data structure, which is in that case a simple pool implementation. We create the root and we insert it in the pool. Then indefinitely we will get a node from the pool using a classical pop-back operation. If this operation succeeded, we decompose this parent node into a set of children nodes using the sequential branch and bound operators, branching, bounding, and pruning. And then we will insert those children into the pool. And we do this again and again until the pool is empty, meaning the end of the exploration. So as you can see in this code, we use some statistics in order to count the number of explored nodes and the number of explored solutions to validate the correctness of the approach. So now to add multi-core parallelism to this version, we are going to use the co-for statement of Chapel in order to create multiple tasks that will explore disjoint subtrees concurrently in parallel. And instead of creating multiple pools, one per task, and to encode a complex dynamic load balancing mechanism, you can just rely on the DistributedBag data structure. Also, please make sure to use the corresponding function to push and pop work items from the bag. So it's called add and remove respectively. Okay, and the bag also supports bulk insertion. It's called ALBook, so it's really easy. And as you may remark, for these procedures, we have to specify explicitly the task ID from which the procedure applies, and it is in fact required to ensure the DFS ordering, which is crucial for memory reasons. So regarding the data structural aspect, we are almost done. I will just add some few lines in order to adapt the termination detection of the algorithm. So in this scheme, each task will maintain a status, which is either idle or busy. And the termination of the algorithm is reached when there is a consensus between tasks. Okay, which means that when all tasks are idle. So we are done with this version. Oh, just one thing. For the statistics, we now have an array of counters. Okay, and so this is the multi-core version. And finally, if you want to extend this version to handle multi-locale with multiple tasks, it's very straightforward using this bag. You just need to specify at the initialization that you use multiple locales, okay? And then, as usual in Chapel, you can use nested coforwards to first handle the locality using the on clause and then multitasking. And for the remaining, it is automatically managed by the DistributedBag data structure. So for example, when you call back.remove task ID, it should remove an element from task ID from the calling locales. Okay. And I also forgot to mention that the work stealing mechanism also works at the multi-locale level. Obviously, to make my code run, I should update the termination criterion to multi-locales, but I will skip it because it's not the key point of the presentation, and I will save some time for the remaining of the presentation. For the experimental evaluation, I pre-built Chapel and also pre-compiled the code in order to save some time. So let's start with the sequential version of the branch and bound. Okay, so it took 4.3 seconds. Now in multi-core using 10 tasks, okay, we note a substantial speed up, and also we can see that the workload distribution per task is very fair. Each of the tasks explore approximately 10%, which is expected, okay? And you can also note the correctness of the explorations. Now in distributed setting, I will set a bigger instance because we have more computational resources. TA15, and for one locale first. Okay, 5.2 seconds. Now we're using 2 locales. Okay, it's almost twice faster, and you can see also that we have a fair distributions. Using 4 locales, it's even better, and for 8, okay, the same. You see, we have a substantial speed up each time, and so this demonstrates the high efficiency of the data structure and its work stealing mechanism at both intranode and internode level of parallelism. In this slide, you can see some experimental results we had in a previous work where we investigated the strong scaling efficiency of the approach, which is in fact the speed up when you keep the same problem instance but increase the number of computational resources. So we use the Meduxina supercomputer, whose nodes are composed of two 64-core AMD Epic-ROM CPUs and interconnected using the InfiniBand network. You can see that we achieve 50% of speed up using 400 nodes, which is a pretty nice result because it is a challenging scenario. Indeed, 400 nodes represent more than 51,000 of CPU cores, and so as many pools inside the data structure. To conclude this presentation, we have seen that DistributedBag is a powerful tool to implement tree-based algorithms at scale. We demonstrated its performance on the branch and bound method applied to the PFSP. And for the future perspectives, we plan to look for ways to remove the task ID from the implementation because it can be restrictive in some users' applications. We also hope to collect users' feedbacks in order to improve the existing features and maybe add new ones. And we also have to do some performance optimization and tuning. So here you have some references, and thank you for your attention.
Thank you so much for the presentation. So we're gonna move to the Q&A session. So if there is any questions, you can unmute yourself and ask the question, please. So I believe that Guillaume is here present in the call, so he can address the questions. There are also some questions in the chat box. So if there is not any, so I can go forward and ask the first question, and then if you have other questions, then you can please unmute yourself or put that question in the chat box. So the first question is for Guillaume is from Luca. Very interesting. Branch and bound is a very common pattern in algorithms using interval arithmetic. How composable is this framework? I wonder if I could use it to define an interval root finding algorithm and let the framework handle the tree search.
I think Guillaume lost his connection, but as I am one of the authors, maybe I could answer. Yeah,
please go ahead. Thank you.
Yes, I think it's possible, but I think Luca would have to define what is its subproblem in the what's the interval and how it would branch to generate more restricted intervals. If this one doesn't help, the more general one, the chop, the one I presented, it's based on intervals, so it should be easier with the chop version of it. Because this one is an extension of the chop that doesn't work only with intervals, any kind of problem. So I think it's possible, but it would have to work with the subproblems and what's the branch stage, how could he define the node as unfeasible or feasible in the termination criteria. So I think, yeah, yes, it could be used.
Cool, thanks. So is it easy to like overload for like if I define my class for interval root finding problem to like overload how to do the branching, how to specify the termination condition?
These I think Guillaume would have to answer. Yeah, maybe you have to define by hand some part of the termination and so on. To be honest, yes, I think you would have to do this by hand.
Okay.
But it's something that Guillaume would answer with more more details. But would not be difficult to be honest.
Okay, cool. Thank you.